Hello, my name is Cameron Lester, and welcome to our next video in the Monte Carlo video series. In this video, I will introduce the simple Monte Carlo model, an example of this Monte Carlo model, how we may emulate this example in R, and I will pose issues with the simple Monte Carlo model and further improvements that we will address in future videos. Section 1, the simple Monte Carlo model. Our goal with the simple Monte Carlo model is to estimate the real integral of g of x. Say that we have a random variable x with density function f of x. Then, we know that the expected value of g of x can be represented by the following integral of g of x with a density function f of x. If we draw a random sample of x1 to xn from this density function f of x, we may then use the mean of g, taking this sample into account, in order to estimate the expected value of this function. So, if we choose an appropriate density function f of x for our desired integral, we can then treat the expected value as an unknown parameter that is estimated by our mean g taking x from random samples. This is very useful for finding the estimates of integrals that are otherwise difficult to directly calculate. There are a few properties of this estimator to consider. First, the expected value of g must be finite for g bar to be a consistent estimator, meaning that g bar approaches the expected value of this function g as our n approaches infinity with a probability of 1. Also, if the expected value squared is also finite, then our estimator g bar of n will be approximately normally distributed by the central limit theorem. Section 2. Monte Carlo example. For this example of using Monte Carlo for integral estimation, we will estimate the integral of x to the power of 9. We'll take g to be x to the power of 9 and f to be the uniform distribution on the intervals 0 to 1. Then, our expected value of g of x may be represented by the following integral, taking g of x with a uniform distribution. In order to solve this, we will use the following algorithm. First, we will generate a random sample of x1 to xn taken as independently and identically distributed from the uniform distribution on the interval 0 to 1. Then, we will find g bar of n by taking the mean of g of x using this sample. This process can be applied to many different integrals. However, it will require changes in the values of a and b of the uniform distribution to address different limits. Section 3. Monte Carlo in R. To solve this example in R, we will create a function. This function will take in a sample size of n, and then create a random uniform distribution of this size. We will then take this sample and use it to calculate our g of x and return the mean of g. We will replicate this function 2,500 times with a sample size of 10,000 in order to get our Monte Carlo estimations for this integral. Then, we will plot these estimations in a histogram against the true value of the integral in order to see how successful we were. After graphing these results on a histogram and displaying the true mean of 0.10 against the results, we can see that this estimation seems pretty good. There appears to be a bit of a wide variance, and of course, on bad days, our value seems to linger very far away from the true mean. However, overall, this seems pretty viable. Section 4. Issues with the simple Monte Carlo model and further improvements. There are several issues that we may face when utilizing the Monte Carlo method. First, we won't always have an efficient estimator for a given integral, which is especially a problem when using complicated real-world applications of the method. Second, finding an appropriate distribution function to sample from is difficult in some cases, as it may be hard to predict the correct distribution model to use for any given estimator. Third, the variance can be very high on bad days, as we saw in our example. Therefore, we will need to either find solutions or creative workarounds to these problems. Our future videos will address these issues by introducing general variance reduction strategies, including important sampling and control variates for this Monte Carlo method.